Alright, so today I'm gonna be explaining this important paper with the title Rethinking Kernel Methods for Node Representation Learning and Graphs. This NeurIPS paper in 2019. Graph kernels are kernel methods measuring graph similarity and serve as a standard tool for graph classification. However, the use of kernel methods for node classification, which is a related problem to graph classification, graph representation learning, is still ill-posed. And the state-of-the-art methods are heavily based on heuristics. So we present a novel theoretical kernel-based framework for node classification that can bridge the gap between these two representation learning problems on graphs. Our approach is motivated by graph kernel methodology, but extended to learn the node representations capturing the structural information in a graph. We propose a novel mechanism for node feature aggregation and data-driven similarity metric. This is an overview of kernel-based framework. You have some learnable kernel, and then we create the loss, and the inference is different. Node classification is ill-posed, so let's see why. We propose a learnable kernel-based framework for node classification. You know the graph kernels between two graphs to see how similar they are. And for representations on learning, this is just one of the approaches using encoder-decoder framework that will create this loss. So encoder-decoder function, it contains an encoder which projects each node into an m-dimensional vector to generate the node embedding. This function contains a number of trainable parameters. S is a pairwise similarity function defined over the graph, and L is the loss function. So this function evaluates the quality of pairwise reconstruction between the estimator encoder-decoder and the true value between two nodes. So we can replace this encoder-decoder with just a kernel function, k theta. Because it's faster, it's easier to do this. And however, there exist two technical challenges. Designing a valid positive semi-definite kernel which captures the node feature is non-trivial. And it is impossible to handcraft a unified kernel to handle all possible graphs with different characteristics. So we introduce a novel formulation to replace k theta. Inspired by the graph kernel and the mapping kernel framework, our key idea is to decouple k theta, this k theta. We want to decouple it into two components. A base kernel, which is positive semi-definite to maintain the validity, and a learnable feature G to ensure flexibility of the resulting kernel. So we can write the kernel, the base kernel, like this. Now for implementation of feature mapping function g theta, we can use this Nadaraya-Watson kernel average. Because the function g aims to project the feature vector of each node to a better space for similarity measurement. The idea is that connected nodes usually share some similar characteristics, and thus changes between nearby nodes in the latent space of nodes should be smooth. So, inspired by this kernel smoothing idea, we can consider G as a feature smoother, which maps X into a smooth latent space. And this P, you may say, this is just a mapping function to compute feature vector of each node. We can just let it to be X sub V. So our final feature mapping function G is like this. This M is an indicator matrix which is equal to 1 if Vj is a th hop neighbor of V sub I, otherwise it's 0. So in node classification, we train kernel to minimize the objective on the triples. Because we aim to measure node similarity with respect to class labels and their hand-designed metrics. And we define the pairwise similarity like this. So if Vi is our anchor point and Vj is a positive of the same class as the anchor, while Vk is negative, so this is negative, this is positive, then we can define this loss. This is a simple triplet loss that you know from contrastive learning, from machine learning in general. And then we can do a nested nearest centroid classifier which extends the k nearest neighbor. This is one classifier. Another classifier could be softmax classifier. So they did experiments on these datasets, Cora, Sightseer, PubMed, because they are good for node classification. These are the results, the accuracy in terms of the percentage of accuracy. And they compare, for example, graph attention or graph convolution to their method. And if you change the aggregation settings of the aggregation, you get different results. And this is TSNE visualization to see how good their method is in comparison to graph attention and graph convolution.